Have you ever wondered how birds skillfully navigate the air or how ships cut through water? To understand these phenomena, we need to dive into the world of fluid dynamics. This fascinating field of study is pivotal for making sense of a myriad of natural and man-made phenomena. Picture the elegant dance of a bird in flight or the powerful surge of a ship slicing through the ocean. Imagine the swirling patterns of weather systems, the gentle flow of rivers, or the rush of blood through our veins. All these are governed by the principles of fluid dynamics. This field helps us comprehend how liquids and gases move, interact, and influence our world. It's a world of motion and energy, of force and resistance, of balance and change. The key to unraveling these mysteries lies in a complex mathematical equation known as the Navier-Stokes equation. The Navier-Stokes equation is a mathematical tool that helps us predict and understand fluid behavior. It's like a language of fluid dynamics, each symbol whispering secrets about the dance of liquids and gases. Let's start by introducing the equation itself. Vt plus V of V equals sign P plus N2V. Now don't let this symphony of symbols intimidate you. Each one has a unique role to play. The first player in our equation is V, representing the velocity vector of the fluid. Velocity in this context is a three-dimensional concept, taking into account not just speed but also direction. So V gives us the fluid's speed and its path at any given instant. Next we have T, which stands for time. Fluids are always moving, always changing, and the variable T allows us to track these changes as they happen. It's the ticking clock of our equation. Then there's P, symbolizing the pressure within the fluid. Pressure is a force applied over an area, and it plays a crucial role in influencing how fluids move. Higher pressure often pushes fluid towards areas of lower pressure, creating motion. Our next character is nu, denoting the kinematic viscosity. This is a measure of a fluid's resistance to flow. Think of it as the fluid's stickiness. Higher viscosity means the fluid is stickier and flows more slowly. Finally, we have the gradient operator. This mathematical tool helps us understand how quantities like velocity and pressure change across the fluid. It's like a magnifying glass, revealing the tiny shifts and changes happening within the fluid. So there you have it. The Navier-Stokes equation isn't just a string of symbols, it's a story of fluid motion, told through the language of mathematics. Each component, velocity, time, pressure, viscosity, and the gradient, plays a critical role in this narrative. Understanding each component of the Navier-Stokes equation is the first step in decoding the fluid motion. Now that we know what each component of the Navier-Stokes equation represents, let's see how they interact. Diving into the equation, we first encounter the term Vt. This represents the rate of change of velocity with respect to time, which is simply acceleration. This tells us how fast the fluid is speeding up or slowing down. Next, we have Ve dV, which describes the convective acceleration. This is the acceleration due to the fluid's movement along with its flow. Imagine you're on a roller coaster, feeling the rush as you're carried along with the ride. That's convective acceleration. On the right side of the equation, we begin with P. This represents the negative pressure gradient. In fluid dynamics, pressure doesn't act uniformly but varies across the fluid. This term tells us how pressure changes across different points and drives the fluid from high-pressure areas to low-pressure areas. Following this, we have N2V, the term representing the viscous forces. This is where the viscosity, or stickiness of the fluid, comes into play. When you pour honey, it flows slowly due to high viscosity, whereas water, with its low viscosity, flows quickly. Viscosity resists the flow and creates a kind of internal friction within the fluid. Lastly, we have the equals sign. This is not just an ordinary equals sign, but a symbol of balance. It tells us that the acceleration of the fluid, left side, is balanced by the pressure gradient and viscous forces, right side. The fluid doesn't spontaneously speed up or slow down. Every change is a response to the forces acting on it. So, the Navier-Stokes equation is a statement of Newton's second law, adapted for fluids. It states that the sum of forces on a fluid element, pressure gradient and viscous forces, equals the change in momentum, acceleration of that element. As we can see, the Navier-Stokes equation captures the intricate dance of forces at play in fluid motion. Despite its utility, the Navier-Stokes equation holds a deep mystery that continues to baffle mathematicians. Despite being a cornerstone of fluid dynamics, a riddle lies at the heart of this equation, a riddle that has yet to be solved. This riddle is known as the Navier-Stokes existence and smoothness problem. In simple terms, it's a question of whether solutions to the three-dimensional, incompressible Navier-Stokes equation exist, and if they do, under what conditions. This might seem like a very academic problem, but it's actually incredibly important. After all, if we can't be sure that solutions exist, or if we can't predict what form they'll take, then our ability to model and predict fluid behavior becomes significantly limited. The existence and smoothness problem has been a thorn in the side of mathematicians for decades. It's so complex, so difficult to crack, that it's been classified as one of the 7 Millennium Prize problems. These are a set of unsolved problems in mathematics that were announced by the Clay Mathematics Institute in the year 2000. Anyone who can provide a correct solution to any of these problems is set to receive a prize of $1 million. Yet, despite the allure of such a substantial reward, the solution to the Navier-Stokes existence and smoothness problem remains elusive. It's a testament to the complexity of the problem and the sophistication of the mathematics required to tackle it. The Navier-Stokes equation, despite its importance and widespread use, continues to be a subject of active research. It's a symbol of the profound influence of mathematics on our ability to model and harness the natural world. Yet, it also serves as a reminder of the vast mysteries of the universe that remain to be uncovered. The Navier-Stokes equation, while a powerful tool, reminds us of the vast mysteries of the universe that are yet to be uncovered. The Navier-Stokes equation is not just a theoretical construct, it has practical implications in many industries. This fundamental equation in fluid dynamics has shaped our world in more ways than you might realize. Let's start with engineering. The principles of fluid dynamics, governed by the Navier-Stokes equation, are at the heart of designing efficient vehicles. Whether it's a car cruising down the highway, a submarine diving into the ocean, or a plane soaring through the sky, understanding how fluids behave is key. Engineers use this equation to analyze the drag forces acting on these vehicles, optimizing their design for maximum speed and fuel efficiency. Moving on to meteorology, the Navier-Stokes equation is instrumental in predicting weather patterns. From the formation of clouds to the path of hurricanes, the motion of air as a fluid is central to these phenomena. Meteorologists use this equation to model the Earth's atmosphere, helping us predict and prepare for severe weather conditions. In oceanography, the equation helps us understand the movement of ocean currents, which carry heat around the planet and play a major role in our climate. Oceanographers use the Navier-Stokes equation to model these currents, shedding light on their impact on global warming and marine life. Even in the field of medicine, the Navier-Stokes equation finds its application. For instance, understanding blood flow is crucial for diagnosing and treating cardiovascular diseases. Medical professionals and researchers use this equation to model how blood, a complex fluid, flows through the body. From these examples, it's clear that the Navier-Stokes equation has a wide-reaching impact, touching many aspects of our lives. It's a powerful tool that allows us to predict and understand the complex behavior of fluids, whether it's the air we breathe, the water in our oceans, or the blood in our veins. From predicting weather patterns to designing efficient vehicles, the Navier-Stokes equation plays a pivotal role in our everyday lives. Its profound influence on our world is a testament to the beauty and power of mathematics. Fluid dynamics, as represented by the Navier-Stokes equation, is a beautiful blend of mathematics and nature. It's a dance of numbers, symbols, and variables, choreographed to describe the movement of liquids and gases. Each term, each symbol has its own role to play, contributing to our understanding of fluid behavior. The Navier-Stokes equation is a testament to the elegance of mathematics, a language capable of capturing the complexity of the natural world. But it's not just about beauty, it's also about challenge. Despite its widespread use, the equation still holds unsolved mysteries. The quest to fully understand its properties is an ongoing journey, a challenge that continues to captivate mathematicians and scientists around the globe. In this journey, we're not just solving an equation, we're trying to decipher the language of nature, to understand the logic behind the fluid motion that surrounds us. As we continue to explore the depths of fluid dynamics, we are reminded of the power of mathematics to unlock the mysteries of the natural world.